don't mind. Did you hit it? All right, let's begin. Dear Heavenly Father, we thank you for today. I thank you for these students. Just pray you help us to use this time wisely. Just that you be glorified, Lord. In your name I pray. Amen. Okay, so I also want to, just before I answer your homework questions, which I'll try to spend the bulk of today on that, but just spend 10 minutes or so talking about some examples in my notes. If I haven't posted this already, I will sometime post this soon in course content, so you can look at it there if you want. This is my old school Calculus 2 notes. I'm not sure if it's posted. I think it's posted on my website, but anyway, just to be sure, I'll post it in course content for you guys. So I think maybe you'll understand these examples better now that you've been working with Taylor series for a little while, right? We looked at these a little bit before, but I just want to take a second and look at them again. This is a fifth order polynomial, a quintic, and I'm approximating it with a second order Taylor. That's supposed to be 0, 0, 0, 0. Anyway, the quadratic here is 2 minus 30x squared. Now, you're like, okay, so if you're using the quadratic, why are you looking at the third and fourth derivatives? Well, simple reason. If I look at the third derivative, I get this. If I look at the fourth derivative, I get that. And if you focus on this interval, say minus 1 to 1, you can see that the fourth derivative is positive there, right? It's about 360 plus or minus 72. It's positive, which means that the third derivative is increasing, right? Which means the third derivative of minus 0.1 is less than the third derivative at x is less than the third derivative at 0.1. So I can use calculus to come up with bounds on the third derivative by looking at the fourth and gaining geometric data about it there, right? So there you go. The third derivative is bounded between 92.4 and minus 20.4. So if my x is within 0.1 of the origin, my third derivative is bounded by 92.4. Now I can use Lagrange's formula for the remainder to put a bound, basically to construct an error bound on what's involved in replacing the fifth order polynomial, the quintic, with this quadratic. And I get that the error is at most like 0.123 as it happens. And then what I did below is I just graphed the quintic, the fifth order polynomial, as well as the quadratic. And so the gray here is the error bound, which is illustrative of Lagrange's formula for the remainder, the error estimate, which follows from that. And so the red is the actual function, the green is the approximate, the quadratic Taylor polynomial, and as you can see, there's very good agreement. And in fact, the Lagrange remainder is actually quite generous, maybe too generous. Yeah. Here's a bigger picture. Here's the quintic, which is all kind of lumpy and interesting in the large scale. But if you're close to the origin, you see that quadratic does a really good job of approximating it, right? And I can tell you specifically how good the approximation is by studying Lagrange's formula for the remainder, which is pretty cool. I have a couple examples here for sine x where I show, for example, sine x is within x to within 0.01 if you're like between about 24 to basically plus or minus 20 degrees. That's in here. See here. Oh man, look at that. There's an example I want to show you guys. I thought it was after that. It must have been before here. Yeah, here it is. Another nice example, just in terms of like, a lot of times the way series approximation are used theoretically is more like this. So in Einstein's relativity, special relativity, you derive this formula for energy, m naught c squared divided by the square root of 1 minus v squared over c squared. Now this is an interesting formula because it has domain plus or minus c, like c not included, right? That would give you division by 0. So that's basically what happens if you wanted me to give you a synopsis of what special relativity looks like. Basically, you take classical mechanics and a lot of formulas get multiplied by this gamma factor, where gamma is in fact just 1 over the square root of 1 minus v squared over c squared. The gamma is approximately 1 if the velocity is very small compared to the speed of light, and it becomes infinite as the velocity approaches the speed of light, and that's the modification pragmatically to a lot of formulas. Anyway, if you differentiate this with respect to v, you get this 3/2 power like that, right? And then you can say, okay, well, I'm going to look at the power series expansion of the energy as a function of velocity. What does that look like? Well, that looks like this. It looks like E of V is m naught c squared plus 1/2 m naught v squared plus 3 m naught over 8 c squared v to the fourth. And this is actually very interesting because the second thing is something you already know. That's the classical kinetic energy, 1/2 mv squared, right? But then before that, something even lower order, there's this pesky constant term sitting there. Well, what is that? This is the famous mc squared, right? This is that thing that Einstein found, which is that there's this rest energy, this huge rest energy. Sorry, the word huge has become tainted of late. But this enormous rest energy, there we go. Tremendous. I think he says that too. Yeah, you're just teasing me. He sort of has we need to come up with new words for large things. See, these are all things I could see him saying about anything he does. I don't know who I'm talking about. But yeah, whoever I'm talking about. Let's see here, m naught c squared. This is the rest energy, right? And that is very large compared to this, because c squared is, well, big, 3 times 10 to the 8th. C is the speed of light here. And so this is interesting in a sense that power series allow us to understand how one formula relates to another. It allows us to take a given physical theory and approximate a variable and understand how it interrelates to other theories and certain approximations, all right? In this case, in the case that if the speed of light is if the speed of your object is much smaller than the speed of c, much smaller than c, then this term is like tiny, all right? If v over c is very small, much less than 1, then this is something like 3m naught over 8, c squared times something very small. So this is negligible, and it's just these two terms that are dominant. This thing finds a way of hiding itself in everyday physics, right? Because most things, there's not some kind of interchange of nuclear energy. But when there is, we notice it. Pretty much. Anyway, here's the classical kinetic energy in green. As you can see, the velocity is not bounded, it just goes on and on. Whereas the red is actually the relativistic energy curve, which has speed limits plus or minus 1 in my current graph. Anyway, that's, I think, an interesting application of the series idea. By the way, one of the great mysteries in physics is this phenomena of decoupling. Do you guys know what decoupling is? I don't think it's something that's been popularly exposited much, but there's this thing that happens in physics where you can study one particular sector of physics without really facing significant interference from the next sector. Like, we can study classical mechanics to a very good approximation, and it does just fine. The fact that special relativity is out there and totally modifies everything doesn't matter too much because it only really applies to very fast things, right? When you study the chemistry of atoms, the things that happen with the electrons, like the valence structure, is more or less decoupled from the nuclear structure. There's another story that goes on with the binding of neutrons and protons and stuff like this. This keeps happening, that different energy levels are somehow decoupled. So you can study one part of physics at a time without it all being intertwangled with the other stuff, like intertwined with the stuff which is at the other level that you're not at. Why should nature be so arranged that we can study it level by level without understanding the next level? Well, people who believe in the anthropomorphic principle basically would tell you it has to be that way because we can study it. Well, if you find this to be a satisfactory explanation, you're a more creative thinker than I am. I just find it to be evidence that God has created a universe that is full of things for us to study. He's made these things accessible in this way precisely because he wants us to enjoy creation and to control it as he told us. Mathematics is no different. Mathematics is part of his creation. Part of the reason that mathematics is so understandable is because God has created it to be such. That's my view, of course. I mean, an atheist can study mathematics just the same, right? Their math won't probably be wrong, but I don't think they appreciate it the same way we do. Yeah, so whatever. All right, so my next example, and then I'll get to your homework, I promise, is this is Newton's universal law of gravitation, right? GMM over r squared basically says the force of gravity is reciprocal. It's inversely attractive to the distance between the centers of mass of the gravitating bodies. In particular here, if this is the Earth, it's a very nice Earth, right? And this is a mass which is being gravitated by the Earth. Well, the force of gravity depends on the distance from the mass to the center of the Earth, right? Assuming the Earth is not lumpy. And, I mean, it's uniformly distributed in mass, whatever. So if you look at that, the r is equal to the radius of the Earth plus what's called the altitude, right? So I can look at the gravity as a power series. I can expand it in terms of the altitude variable. And when I do that, all right, I get, what do I get? I get f of h is that. I get f prime of h is gmm over r plus h cubed. The derivative is decreasing. So lo and behold, the first order, the linearization of gravity, is just this. F of h is minus gm over r squared plus or minus 2 gmm over r cubed h. I'm not sure the plus or minus really needs to be there. I just put a plus probably. If it was, I forget what I meant by h here. Maybe I'm thinking of something. I'm not so sure about this plus or minus. Anyway, what is Lagrange's formula for the remainder basically tells you that if you ignore this term, right, and you just say gravity is equal to this piece, what's the error in that? Well, the error in that is essentially what Lagrange's formula for the remainder says is the error in that is essentially as big as this. This encapsulates the error just using this term alone. I mean, this term alone encapsulates the error in just truncating the series here. Because, of course, if you go on, there's infinitely many terms, right? What is this first term? Well, if you calculate g, mass of the Earth divided by the radius of the Earth squared, that's about 9.8. This is the little g, 9.8 meters per second squared. That's what that's coming from. So in other words, the 0th term is just minus mg. And it goes down, right? The error in that is this. And now I hope you understand what I was talking about before. That's Lagrange's formula for the remainder. You know what that is now. This is an ugly example compared to your homework, but you can still do it. And if you plug the numbers in here, and you look at the acceleration, divide by little m, all right? If you're at an altitude of 1,000 meters by my calculation, you've got the true inverse square law to within 0.0031 meters per second squared. At 10 kilometers, you're within 0.031 meters per second squared. At 100 kilometers, the error is about 0.3 meters per second squared. So, I mean, in as much as the flight of planes that are commercially available is concerned, F equals mg is pretty good. Yep.
Well, the force equation, is it the same as F equals ma?
Yes. So divide by m, and then you get a equals to g big M over r squared. That's about 9.8. If you plug in the gravitational constant g, which we haven't talked about yet in physics, but maybe today. Wait a minute. Better not happen today. Maybe tomorrow. Yeah. Anyway, I'll put that away. I just wanted to point out to you guys that power series have both theoretical and explicit numerical application to real physical problems, right? And so the reason you're studying these in part is so that you can also make these applications to whatever science it is that you're studying. And also the reason we like to study like Lagrange's formula for the remainder and this stuff, it's not just to be mean, it's because if we're going to use Taylor polynomials to approximate functions, it begs the question, how close is your approximation, right? Lagrange's formula for the remainder and the associated theorems give us a specific way to quantify how far off we are by truncating the infinite series at just a few terms, which I think is cool. But you can disagree. But you'd be wrong. But you could disagree. Let's see here. But again, you'd be wrong. Let's see here. Okay. Let me just talk through these for you. So number 43 in section 12.6 said find Lagrange's formula for the remainder. I would just say that this kind of problem is kind of boring. I'm sorry I signed it. I didn't understand what the problem was. It's weird. It's a weird problem to me because all he wants you to do is to like use Lagrange's formula for the remainder and to actually work out the n plus 1th derivative, plug in c, cancel stuff, and that's the answer. Okay. Yay. I don't know. What's the point of this? I guess the point is if I have x is bounded a specific thing, then I could maybe do something with this formula. To me, in 12.6, the questions which are far more natural and interesting are 25 through 32. 25 through 32 are interesting. More interesting questions involving Lagrange's formula for the remainder. Somebody also asked me about number 58 in 12.6, which is this. Number 58 in 12.6 is this. This is number 8 in 12.6, right? Sorry, I'm doing all your homework for you. But remember, the point of homework is to understand the math. It's not just to get points. So if we understand the math together, I don't much care if you all get the points. The point is that you understand the math. 12.6 is a barren wasteland of theory. Like if you just look at 12.6 on its own, it doesn't have many toys. I want you to be able to use the toys from later in the chapter to do 12.6 problems if you want to. Because it's important to me that you learn the stuff in 12.9 as deeply as you can. So the more experience you get with that stuff, the better. So it's fine with me. If you solve number 8 in 12.6 like this, like if I want to find the fifth Taylor polynomial for x times cosine x squared, personally the way I'm going to do it is I'm going to look at the Maclaurin series like this. I'm going to multiply that out. I'm going to go, okay, so the fifth order Taylor polynomial is just up to fifth order, which is just that, done. Now, if you're like the person who just sighed and you've actually calculated all 5 of the derivatives, this could sting a little. Don't feel bad. Differentiation is always good to get more practice at differentiation. It will come in handy in the long run. Any questions about what I'm saying here about that? Do you see my sneaky way of viewing the problem? Yes, sir. How did I what?
Cosine, isn't that the that's pertaining to the even side of the equation, like x squared, x plus x?
Well, yes, very good. Indeed, cosine of x squared is an even function, true. But I'm multiplying that by x, right? So it's odd. The net function there is odd. You'll excuse me if I eat a candy. It helps me not cough. Now this one here, again, if you're in 12.6 mode, you probably would just differentiate this thing, hopefully after you do this. I mean, I think we all should agree that this should be done first. If you're differentiating that straight up, no, incorrect. You should have learned, at least from your study of logarithmic differentiation, that when logs are involved, you should take advantage of their properties. And sometimes even when they're not involved, you should get them involved so you can take advantage of their properties. So let's see here. I mean, logarithms are like rubes of the mathematical world. They're useful idiots, you know. Let's see here. It doesn't seem fair. Oh well. But anyway, so if we get that, then you differentiate, right? Then we use geometric, and then collapse things together. Something really cool happens. This, when you add the series, that's 0 when k is odd, right? So you just get this sum of even terms. And then to get back to what you have up here, you have to integrate. So you can derive this using geometric series techniques with a minimum differentiation and pattern finding. Yes, sir?
Why is it adding after you differentiate? Should it still be negative?
The chain rule says that I have to multiply by the derivative of the inside function here, which is 1 minus x, which has the very boring derivative of minus 1, and then minus a minus gives me plus. But good question. Other Other questions about this? Okay, these are the first questions the earlier section had. I just thought I'd share them with you since I already have them written and it doesn't cost us much time to look at my solutions. So what do you guys have questions about? I'm not going to answer number 66 of 12.6, but I will tell you this about this. There's a typo. The qth partial sum should be what? It should be the sum of k equals 0 to q of stuff. I forget what the stuff is, but fine. Just make me work so hard. Oh, 1 over k factorial. That was very hard. Fine, I guess I can afford that much mental effort. He has an infinity there. He says the sum k equals 0 to infinity. And it seems he's saying the series is the qth partial sum. That's just a typo. With that modification, the problem makes sense. Yes, sir.
On that same problem, it says something about a positive integer less than 1.
Yes. How many of those are there? None, right. So if you can show that existence, that being a rational number implies that there's a positive integer less than 1, that's an absurdity. Therefore, the exponential is not a rational number, which is what you're trying to show. The number e is not rational, is the point. It's a proof by contradiction, so like.
Number 56, can you use stuff from 12.8?
Number 56. In which one? 12.6, number 50. What? Did you say 58 or 56?
56.
56. Natural log of 1 minus ax. Yes?
Oh, I just asking if I can use 12.8 stuff.
Yes, but I wanted to just, let me just talk about that for a second. So Mr. Ahn's question is, was it section 12.6? Number 56. Can you use 12.8 stuff for that? Absolutely. So just to sketch that, what's he saying? He's saying you can go like, okay, so df dx is what? And then I have to multiply by the derivative of the inside function, which is what? Right? So you get minus a over. And then the next move is use the geometric series. All right? That gives you something. And then you integrate the back to f of x is equal to series plus constant, and then show this is 0 or whatever. That's a sketch. I guess I can fill in, well, no, I'm going to stop there. Yep.
Use the Lagrange so that C that shows it's 0 or something.
Just to say what you said again, what you were saying?
Well, you said series plus C on the word.
Yes.
Is that, would you use Lagrange's formula for that?
No. To figure out this, you should have f of 0 is equal to the series, whatever that is, evaluated x equal to 0, plus c, all right, is equal to the natural log of 1. So if your series has all, if there's no constant term in the series that you derive, I think odds are that the constant works out to 0 again. Sorry to be so boring. Yeah. But no Lagrange's formula for the remainder here. By the way, the applicability of this, where the series true, is also derived from geometric series, right? Because you said r is equal to what, ax, right? So you have the absolute value of r is less than ax. Absolute value of r is equal to absolute value of ax. You have to have that less than 1, which gives you what? The absolute value of x is less than 1 over the absolute value of a. And so that tells you the domain for which the series, at least the open interval of convergence for the series you're deriving, works. If we follow the path Mr. An leads us to. And I think that's a good path to go down. I like that idea. Very good. Other questions? Yes, sir. 12.6 number what? Yeah, I mean, I don't know if I really want to talk much about this problem. What's your question about it? I didn't understand it as a whole. I mean, it's pretty, it tells you what to do. It's just not pleasant. I mean, I started this for you guys the other day. Like, I drew the graph in class, right? Remember? This is the example of the function which is smooth at 0, but not analytic at 0. Oh, I'm sorry. Actually, it's slightly different. Yeah, I'm sorry, I'm wrong. I mean, the function I drew is related, right? But what's he done here? So I showed you guys, basically argued that this graph looks something like this, right? For that formula. But yeah, this is an even function, so it's the other side too, right? So that's part A. I mean, I don't know. It asymptotically goes to 1 on both sides. Part B, you're supposed to use L'Hopital's rule to show that for every positive integer n, the limit as x goes to 0 minus 1 over x squared, x to the n equals 0. Limit x goes to 0, what was it? E to the minus 1 over x squared over x to the n, is that right? So you do L'Hopital's rule, right? This is what, infinity over infinity? No, excuse me. 0 over 0, right? So you get what? I mean, you just got to work it out. E to the minus 1 over x squared. What's the derivative of the inside function? Well, it looks like a 2 over x cubed, doesn't it? I mean, there's the first one. And then you keep, and it's still indeterminate, right? Because, yeah, you still got infinity over, well, wait a minute. Oh. Clean it up, I guess. 0. If I bring that downstairs, what do I get? N times just x to the what? N plus 2? Okay.
That doesn't really get you anywhere, does it? Because the bond just keeps increasing. So we're trying to get the bond to decrease.
Ah, yeah. Yeah, flip it. Right. Well, I mean, it's not unusual. You have a L'Hopital problem where if you try to go one way, it doesn't work. If you do the other way, it does. You know, like f over g doesn't work, but 1 over f over 1 over g does work. It's not uncommon. So, Mr. An, you're saying if we try it out like this, then we're in business? Is that right? No. You worked that out? Yes? Yes, okay. I'm sorry? No, right, yes. So yeah, I mean, so after that it starts working. So this is what? L'Hopital's, what we got here? That's infinity over infinity, right? Yeah. So we get minus n, x to the minus n minus 1 over what? Mm-hmm. So then we bring that power upstairs, is that what we do? So that's what? Minus n, x to the power what? Minus n plus 2? Divided by, minus 2e to the 1 over x squared in my current setup. We just keep doing that? And then eventually what happens?
Here with the minus n plus something is positive.
Mm-hmm.
And then it goes to 0.
Yeah, because then we'll have something like 0 over something very large, which is still 0. I won't write down the rest of the solution, but you see where to go. And then the Taylor series of f is, well, the 0 series, right? And that's the annoying thing, is this function is not the 0 function at 0, right? It's 0 at 0, but close to 0. It's non-0, so yeah, this is a function which is smooth but not analytic. It's not well approximated by its Taylor series in any neighborhood of the origin. Other questions? I haven't taught you induction. How do you do induction? To do induction, assume n is true and try to show n plus 1 is true. Yeah. Let's see here. The earlier section had asked that I try to work 12.8 number 14. And 12.6 number 66, I've already said what I'm going to say about that. 12.7 number 34C. Let me see if I think 12.8 number 14 is helpful. Yeah, maybe. I guess it's not due tomorrow. But is this one due tomorrow? I don't think so. It is? Oh, I'm an idiot. I'm an idiot. Number what? I am also confused. Unconfuse me, please.
Tomorrow is, I believe, is the day of this homework, and then Friday is the day of the last homework of this chapter.
Is this one in the last homework, or is this?
This one is in this homework.
Okay, so the last homework is just 12.9, isn't it? That's what's confusing me. I'm being silly. I'm sorry. What's confusing me, guys, is I was working out homeworks that you already turned in yesterday, and that's on my mind, and that's what's messing with my intrinsic numbering. You're supposed to find the interval of convergence of this. How do you do that? Ratio test, yes. Sounds like a good idea. Okay, so this is my a sub k. So you basically look at the absolute value of a sub k plus 1 divided by the absolute value of a sub k, because we have to apply the ratio test to a series of positive terms. This actually will give us absolute convergence on the open interval of convergence, as we know that has to happen. X to the k plus 1 over the natural log of k plus 1. Natural log of k, net value x. All right, so that's equal to what?
So when the problem asks you to find all like values of x when this is valid for, is that talking about finding the interval of convergence?
Yes. Yes, the interval of convergence is the domain for the power series. It's all values of x for which it converges. This won't tell us that. This will at least tell us the open interval of convergence, though, right? And then we might have to think about the endpoints separately. What happens here? You get what? You got yourself an absolute value of x, and you got the quotient of the logs. I think this is a job for L'Hopital's rule, right? So x is fixed. You take L'Hopital's rule, infinity over infinity, right? You get what? You get absolute value of x times what? 1 over k divided by 1 over k plus 1, which limits to what? That just limits to the absolute value of x, right? Because these, if you simplify this, what do you got? You've got k plus 1 over k, which is other 1 plus 1 over k, which goes to 1, right?
Couldn't you just expand ln k plus 1 and then cross out the ln k's? So it's just, or I guess then you'd have ln 1, which is 1 over 0.
What do you mean expand the ln? I'm not sure what you mean by that.
Oh, you're right. It would have to be multiplied in order to
Ah,
add it.
right. Now, there's something to what you're saying, but it would require a little bit of sneakiness. So, like if I did this, if they did ln of k times 1 plus 1 over k, maybe I could get away with something. That would be ln k plus ln of 1 plus 1 over k, right? And so if I look at log k over log k plus 1, then that's log k divided by log k plus log of 1 plus 1 over k. And it's, if you divide that, I mean, if you divide this by, anyway, I think you could start to see plausibility argument that that goes to 1. But let's just L'Hopital. I think L'Hopital's easier. I'm going to erase this before it hurts anyone. Yeah, question. Now that just gives us the open interval of convergence as what?
1 minus 1.
Right, this has to be less than 1. If this is less than 1, then this says what? Ratio test gives convergence of what? Series of the absolute value of a sub k, right? Because I just applied ratio test to the absolute value series. So in fact, we get absolute convergence to the power series on the open interval minus 1 to 1. So the IOC includes minus 1 to 1. And let's see here. I think we still have to check endpoints, right?
Yeah.
So x equals to minus 1. What do you get?
1 minus 1 is the power of k.
Aha. Well, that, my friends, looks what? Yeah, that looks hopeful. That looks like an alternating series. I mean, it is an alternating series. And the b sub k is what? B sub k is 1 over log k. I think it's fairly clear that that is, I mean, obviously k is equal to what? I mean, k has to start at 2 in this series, right? That's the smallest it could start at. 1 is not good. But this goes to 0, and that's positive and decreasing. So you know, 1 is an element of the IOC by alternating series test. Now, how about the other one? Oh, thank you. Yes. How about x equals 1? 1 over ln k. K equals 2 to infinity. This diverges by integral test, I think. Here's my intuition for that. you got stuff like 1 over k, right? 1 over k squared. This is over here. Yeah, you could, maybe that's probably easier. Just forget the integral test, you say do direct comparison. 1 over ln k is less than 1 over k. Ah, right. Thank you. And p equals 1 diverges. Therefore, by direct comparison test, sum of 1 over log k diverges. Yeah. Okay, so in summary, the interval of convergence is equal to -1 included to 1 excluded. There you go. How many of these have I assigned? I've got to write solutions for these. The solution, the answer key is like, the answer key will just be like this. And then it'll be like a word or two. I'm like, so I can't really just copy the answer key and give it to you guys. I have to write my own out, otherwise I feel like I'm letting you down. I was also asked to do 12.734C. Do you guys agree with that request? If you would like to interject another request, you're welcome to do it. You're supposed to, this one is expand sine x and cosine x in powers of x minus a. Show that both series are absolutely convergent for all real x. Okay, so you're looking at the sine and cosine series, right? So basically, you get, when you look at the ratio test, you end up with a quotient of factorials, and like the bigger factorial wins and gives you division by a raw like n plus 1. So ratio test goes to 0 straight up independent of x and a. So that's how you get the absolute convergence for part B. That's not too bad. How to expand sine x and cosine x in powers of x minus a? Well, I think I've showed you guys how to do that the other day, right? 34 of section 12.7. So like, how do you expand sine x in powers of x minus a? Well, you do, right? And that's what? That's sine of x minus a cosine of a plus cosine of x minus a sine of a. And then you can do Maclaurin expansions on those, right? Likewise for cosine. Yeah, cosine x minus a plus a. So that's like cosine of x minus a times the cosine of a minus the sine of x minus a, the sine of a. So that's, and again, these formulas, then you just use substitution with the Maclaurin expansions. You know what I'm talking about? We actually did this the other day with like a equal to 3, right? Right? No? And then C, he says you can rearrange the terms to derive the addition angles formulas. Ooh. Huh. Part C, yeah, part C probably requires some creativity. So I guess what he's saying is you can use the series. Let's see here. He wants us to somehow derive sine of x1. My way of calculating part A makes this whole problem circular. Right? Because I'm like using the adding angles formula to derive, right? Now, do you need to use the adding angles formula to derive these? No. You can, of course, differentiate and use Taylor's theorem directly, right? You don't need to use the adding angles formula to get to these formulas, but by golly, it's a lot nicer to do that. Circular proof is usually the easiest one. Anyway, you're supposed to derive. Fine. All right, let me put that away. Well, anyway, are there other questions? There's no earthly way I can explain to you how to do this homework problem in like 3 minutes. There's no way. You have another question? Yep. What's that? 12.7 what? 20. So here we have sine of pi x. We're supposed to expand in powers of x minus 1. Now here there's hope. So what I do, I mean, you could use, of course, Taylor series, but I'll show you my trick. What I would do is I'd be like, okay, so that's pi of x minus 1 plus pi. And then that is just sine pi times x minus 1 cosine pi plus, well, sine pi cosine of pi times x minus 1 by the adding angles formula, which apparently we're deriving through series methods in problem 34. And so, of course, this is 0. In other words, half the differentiations that you do, you get 0, right? And this is just minus the sum k equals 0 to infinity, minus 1 to the k over 2k plus 1 quantity factorial times pi times x minus 1 to the k power. And then you can clean that up. So we got like minus 1 to the k plus 1, pi to the k, divided by 2k plus 1 factorial, and then x minus 1. And so there's the power series. Which probably wouldn't have been too hard to calculate just from straight differentiation, but, you know. Yes, sir?
Can you subtract that pi, the extra pi that you added from the sine, and just put a negative in front of the sine, and do it with 1 plus down?
I'm sorry?
You know, it says like sine of pi times x minus 1 plus pi.
Yeah?
We took out the pi, put a negative in front of the sine, because that's what pi does. We just skip the adding angles formula kind of thing and go straight to the...
Well, if you know that adding pi changes sine to minus its argument, sure. But if you don't, you can derive that with adding angles formula. Yeah. I mean, if you know that, more power to you. Great. Excellent. Very good. I assume people don't know things. I may be one of those people. I sporadically forget a certain subset of trigonometric facts in a given day. I can derive them all back, but anyway. Oh, I'm sorry. It's time for you guys to go. Or at least you can't stay here. 34 looks fun.